structure at temperatures below the room temperature. So the system is widely investigated in the literature, it's all well established, and this is kind of a phase diagram for the system where the vertical axis tau b represents the attraction strength, lower the value means more attraction, and phi is the volume fraction of these adhesive hard sphere on the horizontal axis, and it has well been characterized using multiple characterization techniques like rheology, light scattering, neutron scattering, and simulations. And we have a phase diagram which suggests that it can be present in different phases like liquid, gel, or two-phase region depending upon where it is located on this phase diagram. Now, so a gel is a system which has some interconnected networks in it, and it can be able to withstand its own weight. So that is what we call it a gel. If you want to know how is it different from a glass, then the perspective would be that a gel forms a percolating network, whereas glass is quite, it's not interconnected in network. It can be either attractive or repulsive, whereas a gel is always attractive in nature. So that is what I call in the literature, and it has been investigated what happens upon shallow thermal changes to the system. It is still yet to understand what happens when the system is subjected to deeper thermal quench. So by deep thermal quench means we are giving it a drastic change in temperatures to temperature from like 40 degree, which is like liquid-like state, to temperatures well below the room temperatures. So that is the goal of the work, to understand the rheology and microstructural changes in this model system of adhesive hard spheres upon deeper thermal quench. So now we have a system in hand, and we know it is thermoresponsive in nature. So we do a simple experiment to characterize its thermoresponsive nature, and we subject it to a temperature ramp down and then up cycle, and we see the corresponding changes in the modulus value, which is G prime and G double prime as a function of temperature. As evident initially at the higher temperatures, the value is quite low. It then increases sharply by almost 5 orders of magnitude, suggesting that it undergoes a liquid to a soft solid like transition. And upon increasing the temperature again, it follows the same cycle. The point of crossover between the G prime and G double prime is often taken as the gel point temperature, but as you can see, the crossover point is slightly different during the heating and the cooling cycle. So in order to have a more well-defined gel point temperature, we seek a refuge in the Winter-Chambin criteria. So Professor Henning-Winter did some pioneering work on gel-like systems, and he came up with this principle that at the point of critical gel transition, the value of moduli will obey an identical power law scaling behavior on applied frequency, and tan delta, which is basically a ratio of G double prime to G prime, will become independent of frequency. So we do carry out this experiment and see the temperature at which the tan delta becomes independent of frequency and G double prime and G prime obey identical power law scaling, and we characterize that temperature as the critical gel point temperature. So this is the temperature where there is the first instance of forming a percolated network, which means that if we have a system of this adhesive hard sphere and we make a box around it, we will be able to cross from one part of the box to the other part by just following the path of the connected adhesive hard sphere particles. So this is the temperature at which there is the weakest path spanning percolated network, and we now have a well-defined gel-like temperature, which is 25.4. So the idea of this temperature is only to characterize the gel point temperature. Yes. No, it has to be just interconnected so that it can span the entire space. So if you see in a larger length scale, it will be a mesh-like structure or a honeycomb-like structure, which is all interconnected in nature. I'm just showing, you can see more fingers here because maybe the system is a little dilute, so I'm just trying to, but if you see in a more larger length scale, it will be, if you see a cryotam image, maybe I can share later, it will be more homogeneous and all mesh-like structure, which is well connected in nature. Okay. Yeah, so it's not fingering or instability is something which is occurring here. This is a schematic, yeah. Yeah, I have published some cryotem images which is there, but this is just a schematic for nature. So the idea was only to characterize a gel point temperature. So we have a reference temperature that, okay, I have a specific volume fraction of adhesive hard sphere and this is my gel temperature. So that we can quantify what is a shallow or what is a deep quench for this particular system. So we take the system, put it on a rheometer and try to give it a shallow thermal quench, which means that we're taking it to a temperature from 40 degree to 25 degree, which is just 0.4 degree below the gel point temperature. We give a step command of change in temperature, but rheometer is not an on and off switch. It takes certain amount of time, which is like 30 to 40 seconds to achieve the target temperature, and the corresponding evolution of modulus is shown over here. We can see that the value is quite low in the initial times and then it increases, crosses over, and then it shows a slow power, slow increase with time. This is quite evident in many colloidal polymeric system, which is a typical signature of aging in the system. So this is something which is well established. Now we subject this sample to a deeper thermal quench, where we give it a change in temperature from 40 to 21 degree, which is around 4 degree lesser than the critical gel point temperature, and see the corresponding evolution in modulus. What we see here is the initial part remains the same as the shallow quench, but after the increase, after the slow increase, there is a sudden change in the value of modulus, and the inset over here is basically an enlarged view of what is happening. We see that the G prime undergoes a drop and G double prime undergoes a slight increase, a slight overshoot over here. So this was something which was very interesting to us. This was never reported in the literature. So we wanted to understand what is happening by doing some bulk measurement using rheology. So the first thing which comes to our mind is whether it is repeatable or not. So let's try it at different temperatures below the gel point temperatures. So first we begin to try with different temperature ramp rates at which I change the temperature. So we begin with very slow ramp rates so that we give the system a lot amount of time to restructure, to reorganize, and then take the final state. So when the ramp rate is very slow, which is below 5 degree per minute, we see that such transition is not observed and the system undergoes a rapid increase, which is signature of liquid to soft solid transition, and then almost insignificant increase. When we make the process of change in temperature quite fast, quite rapid, we see that the system undergoes a drop and it is observed above a ramp rate of 5 degree per minute. So we characterize the time at which it undergoes the drop and plot that time, which is T star, or we also call it the transition time, as a function of temperature quench ramp rate. So we observe that only after a temperature ramp rate of 5 degree, the system undergoes this typical transition and the value decreases with increase in the quench ramp rate. It shows an exponential behavior, but maybe you can try to fit some other model also to it. There is no theoretical evidence to why it should only behave exponentially. We also see the value of G prime at the end of the aging study, which is a duration of 1 hour, and we see that it falls into two different groups. One is very high value, other one being a slightly lower value. So this basically suggests that we have two domains over here. One where the transition is not occurring when the system is undergoing a very slow process of change in temperature, and the system achieves a very high value of G prime. But at higher quenching ramp rate, the system undergoes this transition and therefore the G prime value is low. So using this graph, we can transition or differentiate the system into two regions over here. One where it undergoes the transition and the second one where it doesn't undergo the transition. So after this, we keep the ramp rate constant and change the different temperature at which we do the experiments. So we begin with 23 degree, which is again closer to the 25 degree, which is the gel point temperature. We see that there is a sudden drop in G prime again, which is followed by a slow power law, one at the time of transition and the other value of G prime at the end of the aging study. We again decrease the temperature and do the same study. We see that it undergoes a very sharp decrease in G prime value, and the transition time is noted over this middle graph over here. Epsilon is basically the extent of thermal quench, which is nothing but the difference between the target temperature and the gel point temperature. We further decrease the temperature to like 12 degree, and what we observe is that this transition is no longer sharp now. It's something, some resistance is occurring to the transition, due to which it takes finite amount of time to undergo this transition. But the overall take home message is that it does undergo the transition when you change the temperature drastically to temperatures well below the gel point temperature. The transition temperature over here can be seen to obey a non-monotonic trend with extended thermal quench. We believe that this is due to two contradictory forces acting into play. One, when we decrease the temperature suddenly to very low temperatures, the system dynamics is getting more and more arrested, which would not allow or which would not like this transition to happen. But at the same time, the driving force for this transition is also increasing, which would encourage this transition to occur. So as a result of this interplay between the two competing effects, there is a non-monotonic trend in the transition temperature. So based on the rheological findings, we try to anticipate what might be happening at the microstructural level and how will the system walk upon on the phase diagram over here. So this is a schematic picture which is trying to mention how the system would be spanning the entire phase space. So when we are at shallow thermal quench, we are in the gel-like region, but as we decrease the temperature, we have sudden decrease followed by slight increase, which suggests a nucleation and growth-like dynamics, which suggests that the system might be in the binodal region. As we further increase the extent of thermal quench, there is a sudden decrease in G prime followed by almost insignificant increase, which suggests a very instantaneous transformation like spinodal decomposition. At further lower temperatures like 12 degree, the transition is no longer sharp, which suggests that we are entering into the deep two-phase region where the glass line might be intersecting the two-phase line, and therefore the system dynamics is becoming more and more complex. So this is a brief understanding which we gained from the rheological study. We now go to do some neutron scattering experiments to gain the actual microstructural insights about what is happening to the system upon deeper thermal quench. So we do the experiments at Oak Ridge National Laboratory where we use an Anton pyriometer, and we do the similar experiment where we give the system a sudden temperature shock from 40 to 21 degree, which is the target temperature over here, and we collect the intensity of the scattered light, scattered neutrons as a function of Q, and we plot it as a function of different time intervals. As aging proceeds, how does the intensity curves shift? So initially at 40 degree, the curves are almost on top of each other, but as we subject it to a temperature change, the intensity curves grows and it gains value over here. So we are not the first one to do scattering on this system. It has already been done in the literature, but has been done for shallow thermal quenches, and the data is reported over here from the literature. We can see that the graph is quite similar, that where the intensity is gaining value with respect to time. Other thing to note over here is that there is a low Q scattering, upturn in the scattering, which has not been yet modeled in the literature, and people were not able to find out the reason behind this low Q upturn over here. So we tried to address both the points to understand the microstructural changes at deeper thermal quench and to understand the reason for the low Q small upturn at low upturn in the scattering value. So we use the sticky hard sphere model, which is commonly used to model the attractive system, and we did the simulation and we did the fitting using SAS view. Here is a snapshot of how SAS view looks. It might look very complex, but it's not that complex. I'm just trying to explain what are the different components which we have used to model the scattering data over here. First is the form factor, which contains the information of the size of your particle, which you already know beforehand, and you can also gain insight from micrography or images. We then use the structure factor, which is of sticky hard sphere in nature, and we get a parameter which is stickiness. Stickiness is the same parameter as tau, which was on the vertical axis of the phase diagram over here. And lastly, we also add a small fractal model to it. And using this fractal, so if we use only the form factor and the sticky hard sphere model, we get the red curve over here. But as you can see, the red curve is doing a great job in fitting the attractive strength and the high Q data, but the low Q data it's not able to fit. So we add a fractal model to it, which suggests that we have very small volume fraction of fractals present in the systems, which are quite ubiquitous in nature. So these fractals are basically fractal aggregates which are present in the form of impurities in the system, or you can say that it's always ubiquitous in nature in the system over here. And with addition of this fractal model, we are now able to get a very good fitting to the entire experimental data during the aging time. Now, this is all good and this all works when we are at the early times. What happens when after the transition? We try to use the same analogy to fit the scattering data, but irrespective of any change in the fitting parameters, we're not able to fit it. So next what we try is the volume fraction of the system is fixed at 0.2. We try to increase the volume fraction a bit, which is from 0.2 to 0.35, and we see that we now get a very nice fit between the experimental data and the model using the volume fraction when increased to 0.35. So this suggests that maybe at the microstructural level, the system is phase separating into colloidal rich and colloidal lean regions, due to which the volume fraction locally is increased, and therefore a higher volume fraction of 0.35 is now able to predict the experimental data well. So therefore the scattering data also suggests that locally there is an increase in the volume fraction, and it's the interconnection between the colloid rich phases which leads to the viscoelasticity in the material. So using the fitting parameters, we are able to get a relationship between how the rheological parameters vary and how the fitting parameters of the scattering study varies, which suggests that it's well in hand. At the time where the rheological shows a transition, we have a sudden change in the local volume fraction from 0.2 to 0.35, and it matches well with the scattering study. We also try to investigate if these type of transition can occur when we give it a shear rejuvenation to the sample. So what we do is we take the sample, keep it at a target temperature below the gel point temperature, and shear melt it vigorously to see if the system can again undergo this transition or not. But to a surprise, if you keep on thermally rejuvenating the sample by taking it back to 40 and cycling it up and down again, the system is very much reversible, which is the black and the green symbols. It undergoes the transition. But if you shear melt it at a temperature below the gel point temperature, the transition is no longer observed. The value of modulus is insignificantly growing with time. So this suggests that shear rejuvenation cannot take your sample back to the initial state as a thermal rejuvenation could do it. We also did the scattering SANS experiment to confirm that, and we saw that the intensity curves for thermal rejuvenation and for shear rejuvenation are not identical, which suggests that there is some kind of structure still retained even though you apply very high amount of shearing to the sample. So it's only the thermal rejuvenation which takes the sample back to the initial state, and therefore the transition can be occurring again and again. So with this rheological insights and microstructural insights from neutron scattering, we are now able to understand what is happening to this model system of adhesive hard sphere. At 40 degree, it's at very nicely well homogenized state. As you keep on decreasing the temperature to like critical temperature, we have a weakest or a single path which connects all the particle, and it forms a space spanning percolated network. As you further decrease the temperature, we enter into the two-phase region where the system forms a colloid rich and lean phases, and these colloid rich phases are interconnected by few particles, which leads to the viscoelasticity in the material. As we go further down and decrease the temperature and extent of thermal quench, we enter the two-phase region where we have very rich colloidal rich region, and we need to more understand in that region. So this is what our finding was, and surprisingly, at the same time when our work was published, there was another group who was doing some dynamic simulations, and they came up with a similar idea for a different nanoemulsion system, and they suggested that with change in temperature, the system can span different structures and can form this colloid rich and colloid lean phases in the system over here. So we suggest that our study of rheology and SANS study is a nice proof that the system is undergoing phase separation and entering into the two-phase region, which is also supported by the simulation study in the literature. But we'll be happy to do some more simulation study on this work exactly. So with that, I would like to just summarize the work. We had a system of adhesive hard spheres, which is consisting of silica particles of sphere in shape. We saw that when we take it to a very deep thermal quench, it undergoes a very rapid transition. And this transition is maybe because it is entering the two-phase region. We got some insights from doing neutron scattering that locally that there is an increase in the volume fraction, which suggests that there is formation of colloid rich and lean phases. And the basic take-home message from this work is you can use rheology as one of the first technique to understand your system and to gain some insights which can be used to design some more delicate and costly beam time experiments. So that is the basic take-home message from here. Although we understand many things, there are yet many things for us to explore, and we don't know why is that occurring. Like, why is 5 degree per minute the critical ramp rate above which the transition is occurring, and why is it not occurring before that? Is there any critical time scale of the material which we can utilize to non-dimensionalize the transition time and come up with a non-dimensional time for that? So these are the few questions which we don't understand. This part of work was done with Professor Norman Wagner at University of Delaware during my postdoc, and the funding came from NIST Center for Neutron Research. So this is what I did recently, and this is what I plan to do at IIT Madras. So this is a research theme of my lab, what it would look like. So the idea is basically to understand the microstructure and viscoelasticity of colloidal dispersion. So it's going to be one-stop understanding of all colloidal dispersions. So we begin with controlled synthesis of particles which of varying shapes and sizes, and do a very nice characterization using multiple characterization techniques like rheology, scattering, images, DSC, and then understand the reason for their experimental behavior to gain understanding and have a very nice idea about their performance and their characteristic behavior of these colloidal dispersions. So these colloidal dispersions would on one hand result in some academic knowledge which can be used by other theoreticians to understand their simulation study and gain some collaboration. While this understanding can also be used in many industries, because these thermoresponsive systems and many other systems are widely used as drug delivery agents or in household products. So it will also have some industrial implications as well. So that would be the theme of my work, and hopefully next time I would be presenting some work from my very own students and group. So yeah, happy to be here, and with that I would like to take any questions.
Thank you, Suman and Karen. Questions? Yes.
You had a slide where you were fitting it to phi equal to 0.35.
Right.
That's it. Can we just go back?
Yeah.
Yes. So I was just very curious. This fitting, is it that parameter value? Is it a fitting value, or in your experiments, if you do, I do not know what technique would be used, but is there a technique to actually see what is the volume fraction that will actually fit that, by which you would know the local density of the colloid-rich phase? I just want to know, is it a fitting parameter, or is it something actually correlates with what you see in your
So in an ideal world, we would not use volume fraction as a fitting parameter, because volume fraction is something which we already know, like the diameter of the particle, or the thickness of the particle, length of the particle. So these are the few parameters which we usually don't use as a fitting parameter, because that's like the first principle, you cannot change these parameters. But since in our case, we were anticipating that the system would undergo a phase transition to form some colloid-rich regions, so only for that part, we tried to use volume fraction as a fitting parameter. So this is, so you just click on volume fraction as one of the fitting parameters, and we tried to change that parameter. So it increased, and then we used volume fraction as a fitting parameter. So ideally we would not do, because we know that if we have a system mass is conserved, the system should remain, the total volume fraction still remains the same, the number of particles still remains the same. It's only locally that the volume fraction is increasing, and therefore I use it as a fitting parameter.
Why I've asked that question is that, is it, if in a simulation kind of setup, is it not possible to measure local densities and then see what is the local density, and you don't have to use a fitting parameter,
Right.
but I measure the local density and see what volume fraction may correspond to that, and thereby get also an idea of what is the local density that is happening. Is that possible, or it's not?
From the experiments, it's not possible to say that, but yes, I understand that using simulation, it will be possible, and we'll have one fixed number which will correspond to that low increased density over there. But here we just had an idea that there is an increased density, which would not be an insignificantly large, a significantly large number, but something closer to the value, so because it's only a local increased. So we used just as a guess number over here, as
Just
fitting parameter.
One last question.
Sure.
You were talking about this anisotropic particle. Suppose if instead of hard spheres, one has hard rods or, these kind of other shapes. Would you, what is your guess?
Anticipate.
Would these results would be different or the rheological properties would be different? What is the expectation?
Yes. So this transition, it's very novel and unique. It's not observed yet. So we anticipate that this was because the spheres had more degree of freedom in the terms that was able to diffuse, rearrange and span the space easily, due to which it was able to undergo this transition and form from a very homogeneous arrangement to a spatially heterogeneous arrangement. What would happen in case of rods, what I anticipate is, rods would interact in many different ways like spheres don't. Like spheres would have identical interaction irrespective of where they contact, right? But sphere, if it is interacting in this way, they will have a very strong attraction, and therefore it will be very difficult for them to rearrange and diffuse. And rods can have multiple types of attraction, one being this, which is very strong, other being T-shape or some this shape. So in case of hard rod system, I would expect that the degree of extent to diffuse or the extent to reorganize itself would be difficult, and therefore it won't be easy for that system to undergo the same transition at the same temperatures. Maybe under some very extreme conditions it can undergo that transition, but it wouldn't be that easy just because it doesn't have that degree of reorganization or mobility in the system.
Perhaps multiple time scales also.
Yes, maybe, yes, of course, yes. And diffusivity, rotational and directional, so it would be different.
Ganesh.
Yeah, I have a couple of questions.
Sure.
So the first question is related to the shape, what she was talking about. But my question is, if you know the properties of the nanoparticle changes when the size changes.
Right.
So the interesting, the transition, what you're talking about, is it size dependent? Have you checked, whether the smaller size or maybe the bigger size than this one?
Unfortunately, I have not changed the particle diameter. I have changed the volume fraction only to see if it occurs, and it occurs at different volume fraction at this same fixed diameter. I haven't explored different diameter, but for a sphere of maybe not very big, like this is 30 nanometers, for 100 nanometers also I would expect the same. Maybe at different temperatures, the quantitative value will be different, but the transition would still remain there.
Okay. So the second question is, it's very nice that, rheological data, and then you extracted the structural rearrangement from higher temperature to lower temperature.
Right.
But have you tried the electron microscopic pictures and then freezing the, drying the samples at that temperature, 4 or 5 temperatures, 40, 45, 42, 43, 47, something. So have you correlated your, results from the rheology, and then whether it is matching with the electron microscope? Because you said that, isotropic first, and then when the temperature goes down, and
Right.
randomly is actually kind of
No,
things.
we haven't been able to do that, but yeah, that's a very nice idea to get a very good confirmation about what we are proposing is occurring or not,
right.
but we haven't been able to do that yet. But I'm sure some other student in the group who is continuing my work will definitely try to do that. Yes, but I haven't been able to explore that work. Yeah, thank you so much.
Okay, yeah.
Nice talk. Actually, I have a couple of questions.
Sure.
So, you are getting at nice fitting at 0.35 volume fraction. What if you further increase the volume fraction? What kind of fitting you will get?
So the fitting deviates from the experimental
It will
data.
deviate from the
Right.
And the second is like, this is a hard sphere. If you use microgel particle like soft sphere, right? So mostly that is also temperature dependent size. And you are getting the transition just around 27, 28. That is critical for microgel particles. So what kind of behavior you will expect, like percolated net or something, if you use microgel particles?
So it also, microgel particles, if the same transition would be observed or not is what your question is, right? So Obviously, it's very specific to the system and under what conditions you're doing this study, which results into certain kind of transition, or else it would have been ubiquitous in the literature till now, right? So depending upon the attraction strength also between the microgel particles, as I said, like for the rod particles, if the attraction strength is very large and it wouldn't allow the particles to rearrange by itself, then it would be difficult for the same system to undergo the transition. So it depends upon a lot of factors which results into this. So these are like very short range attractions. So attraction becomes important only when it's very near to the particles, and therefore it can have multiple times, it can arrange, contact, go, and then contact again. So if the attraction is very strong in your system, it will be very difficult to rearrange, diffuse, reorganize to have this kind of transition.
In microgel it will be like,
This is what I expect, yes.
thank you.
No problem, thank you.
Hello, yeah. So I have a question, like actually from the structure factor, actually it should be related with the electron density, right? So can we not know the electron density of this?
Maybe we can go to the electron density, but I don't go in atomistic level to gain the understanding. I normally, the kind of study and we gain insight at more mesoscopic level is what I would say. I haven't been able to explore the atomistic level, and but I'll be happy to collaborate and gain insight on how to gain the electron
Yeah,
density.
so in the fitting this tool SAS view, so do you have a fit parameter of electron density?
No, I don't have a fit parameter of electron density. I only have attraction strength, which is like a collective term for interaction between the particles. So we don't go to the atomistic level to the electron density.
Okay, thank you.
Thank you.
So ma'am, these C18 nanoparticles, are they dispersed in water or in some organic solvent?
So it's an organic solvent which is tetradecane. So we need to have specific kind of solvent in which the octadecanol chains would undergo the disorder to order transition. So any linear alkane solvent can work over here. So this is not water, this is in particular in tetradecane you can use any other alkane solvent to use that, and this would work.
So are the gels stable enough if you overturn the vial in which the gel is, or will it be just stable, or is it just a very highly viscous solution?
So it will be able to withstand its own weight. So you can imagine it's a strong gel. Yes, at temperatures below the room temperatures. At 40 degrees it's very easily flowing, and it remains stable up to years. So yeah, it's a good system to work with. You once synthesize the system and you just keep on doing experiments. It's thermally rejuvenation can work, so you can work again and again on the same batch of samples. So it's easy in that way to work with.
Okay, yeah, with that I think let's thank Kushbu.
Thank you everyone for the questions.
And yeah, I think it's time to move away from coffee, so we'll have Rajesh, yeah. And he's going to talk about ring polymers.
Hello everyone, I am Prajesh Roy from Department of Biotechnology at IIT Madras. I thank the organizers for inviting me today, and I would like to talk about our recent paper on the emergence of self-organized stacks in biodispersed ring polymers. So this is the summary of my slides. So I start with some background on what is the theory of ring polymers and the theory of topological glass. And after that, I will summarize our work on the monodisperse systems, and then we'll move towards the bidisperse systems. And lastly, I will highlight the effect of pressure hysteresis, and then I will end with the conclusion and outlook. So what are the ring polymers and what is so special about it? So basically, for the linear polymers, the theory of polymer dynamics is now well established. People will have the reputation model, which broadly explains the movement of linear polymers. But for the ring polymers, it's not yet very clear how this polymers moves. So one can simply think that ring polymers are basically double-folded linear polymers, and that actually helps to understand some part of the ring polymer dynamics. But in this talk, I will highlight that ring polymers poses a much more complex behavior than one can get from this traditional theoretical approaches. So there are very difficult, where the simulation comes into play here, is that synthesizing ring polymers and studying it is actually very difficult because there are chances of contaminations, and one may get different kind of knots and links that forms during the experiment. So understanding the ring polymer dynamics from a theoretical perspective becomes very important in this aspect. So in biological system, ring polymers are actually has a lot of applications. For example, these plasmids, which are essentially ringed DNAs, and they are very useful in biological systems, and to understand their structure and dynamics is essentially critical. And also, for example, in chromosomes, we have these chromatin parts, which are essentially a conglomeration of multiple DNA regions. And people often try to understand how these particular regions are formed and what are their characteristics. And the recent theory is that these particular regions inside the chromatins are essentially ring DNAs. So they are consisted of different ring polymers rather than linear polymers. And you can see visually that how this linear melt looks like and how the ring melt looks like. And from there you can say that, okay, that it actually looks much more similar for these chromatin ring distributions. So the complexity of the ring polymer starts with the fact that the stress relaxation of the ring polymers are much more slower compared to the predicted from this reputation or different kind of lattice animal models. Basically what happens is, ideally one expects that the stress relaxation from this exponential decay, which is shown here. So in this experiment they have taken a linear and ring polymers, and you can see that although the ring polymers are faster as compared to the linear polymers because they are double folded, but however this theoretical line which is shown by this straight line here actually predicts a much faster relaxation for these rings. However, in reality they are much slower compared to these theoretical predictions. And the interesting part is that if you incorporate more linear polymers inside your ring melt, it becomes slower and more slower, which is kind of unexplained. Recently there are some explanation has come from the theory that you can take part of the ring as a linear polymer, and you can basically create a multi-parameter model for this stress relaxation, which partly explains it. But again, there are a lot of questions that is unanswered. For example, is the threading. So the threading in ring polymers is especially special to the ring polymers. You cannot see this kind of mechanism in linear polymers. What happens is you have two ring systems and they are kind of interlocked into a large length scale topological interactions. For example, you can see here, if you put this ring in between these rings and somehow, and if this rings want to move, it cannot move because this ring is somehow in the way. Although the center of masses are not close enough, which is in traditional glasses, you need to have the particles to be very close together to be packed well. But in this case, the center of mass need not be very close. For example, you can see in this kind of threading, where the rings are actually much far apart. You can take the center of mass of this ring and this ring, they are actually from far away. But they form this kind of knots in between them, which arrest their motion related to each other. So essentially a large scale topological arrest that forms especially in the ring polymers. We call it a topological arrest in some sense. What is interesting is that even if they are arrested, which means their center of mass does not move, themselves the ring can move around. For example, you can show here that this particular ring polymer is in a very threaded environment, but you can see that there is sufficient dynamics around the contour of the ring. This is calling it a treadmill motion, which very interesting because it says that the monomer itself has some fluidity. However, overall the system is in an arrested state. So the question is, what kind of glass one can form when you create without explicitly caging the monomer as one does in traditional glass forming systems. So we basically create a network of these threaded or linked rings, and the question is whether this entire system would form a kinetically trapped state. So this kind of system is called a topological glass, where you take unknotted rings and you trap it inside a network of threading. In this case, we are not focusing on the temperature, density, and this kind of parameters that people normally look for in traditional glasses. We are just wanting to make sure that the threading network is maintained in this case. And so there was an interesting paper that came in which proposed this topological glass idea. What they did was they have a system of ring polymers and a system of linear polymers in a melt, and they pin randomly some of the polymers, and basically they make their motion to be zero. So these particular polymers do not move at all, and the rest of the polymers can move around through this network. And what they observed is that the linear polymers, they can escape this kind of pinned network. However, if you take the rings, they remain particularly caged as compared to the linear case. And this is an example of how this topological interaction is controlling the motion of the linear ring polymers and how it is different from the linear cases. They also figured out what is the typical phase diagram looks like for this kind of glass liquid transition, and they predicted that at a very large kind of ring size, this kind of pinning will not be required. It will form a glass spontaneously. However, they used a very flexible polymers basically, which is why they got a very large ring size. But we thought that what if we don't need such a flexible polymers, what if we introduce stiffness, and what will happen to this kind of phase diagram. Another interesting part of ring polymers is the cluster glass formation. So what happens is, if you take a very stiff ring polymer, which is almost like a plate or a disc, they often form this kind of column-like structures in the melt, which is not very well described, but you can still identify some interesting clustering of where they are kind of stacked against one another. They termed it as a cluster glass system. And this kind of columns, they can interpenetrate with each other, which makes it, which can destroy their columnar structure, but you can still identify some of these column structures. Another interesting part is the ring polymers are depletion effects. So you put ring polymers inside a confined environment, and with a mixture of stiff rings and sort of flexible rings, and you can see that the stiff rings kind of float out of this mixture and they stick to the walls, which means they prefer to be on the walls, which is the depleted region, compared to the inside where it's more flexible polymers are present. So this motivated us to look at the bidisperse mixture of this flexible and stiff polymers, and what the structures looks like when you don't have the confinement after all. So first we studied the monodisperse systems. So in this case, we tried to introduce pressure inside our melts, where the system volume is not explicitly fixed. So we want to see what are the effect of volume fluctuations can take place, how they control the glasses. So we took much smaller ring size than that was predicted by this by the spinning method, and we took about 100 Mars systems. And we used the Kramer-Guest model, which is very traditional for this kind of coarse grain modeling of polymers. And we used a particular angle constraint here, which is basically the Kratky-Porot type modeling. And we simulated the system over a range of stiffness and pressure. And what we wanted to study what are the structures of this system will look like, and what will be the dynamics of these systems. First, we observe that as we increase the stiffness, obviously the system structure becomes more open up. So they start from a globule type of system, then they become a more rod-shaped or much elongated structure, and ultimately they become much more plate-like or disc-shaped. Now we wanted to understand how this threading would, how one can quantify this threading effect inside the rings. So to understand the threading effect, one has to know what are the surface area of the rings are. So we analytically calculate the surface area of each of these rings by basically drawing these crisscross diagonals. And our aim is to show that when this particular overlap happens between the two areas, and how can one quantify that how much of this overlap has happened, and that will indirectly will tell us how much threading is present inside the system. And we have devised an algorithm to calculate this minimum surface area. We take care of these loops. Basically, what happens is drawing these crisscross diagonals often intersect with these large loops, which create some error in our algorithm. So we revised our algorithm so that we can identify loops, especially inside this topology, and we can accurately measure the area of the loops itself. And then we basically calculate how much overlap is happening and how much of these rings that is on the even side and the odd side. But this even odd is basically just name we have given. You can also give it plus minus or whatever. So basically what happens is if it is completely penetrated the ring, then we can say that okay, 50% on the even side, 50% on the off side, which means it is a perfect penetration has happened, so it is a perfectly threaded ring system. And more or less this even side comes along, it will say that okay, this is much weakly threaded system. And we devised a threading parameter which is basically does just that. It counts how many of these monomers are on the even side or on the odd side. And by doing so, we were able to calculate the amount of threading in the system. And we calculated that how many of these threaded polymers are present, which has very high amount of threading, like greater than say 0.75 or so. But which means 75% of the rings have penetrated into another ring. And what you observe is that as our stiffness increases, the amount of threading goes up, which means the more stiff the system is, the more penetration happens and they are much more stable. And to understand this stability, we devised a correlation function which calculates how this threading parameter decays with time, and we showed that by increasing the pressure, one can achieve a very kinetically trapped system where this correlation function does not relax within our simulation time. And we calculated the threading time scale from this analysis, and we have shown that it correlates very well with pressure and as well as with the stiffness as well. So, and we also calculated the diffusion coefficient, and we have shown that this time scale correlates with the diffusion coefficient, or inverse of the diffusion coefficient, and it's essentially linear for the stiff rings. For the flexible ring, we see some superlinearity is present, which might be coming from the packing effects. So basically in flexible rings they are much more globule-like, so their threading effects is low, so their glass formation is more controlled by packing rather than threading. However, for the stiff rings they are mostly linear, which means the threading is actually controlling the slowdown of the systems. So now we come to the bidisperse system. What happens if we take some of the rings inside this melt and I make it into a flexible system? So which was much bigger system, we took 400 rings in cases, and we slowly made some of the rings inside this melt into a flexible with k is equal to 1, and we saw that very interesting structural features emerge. Essentially what happens is we see that the system becomes more fluidous. So the topological glass that is formed at the pure state, it starts to melt. And there is a spontaneous self-organization happens between the stiff rings, and they start to form this kind of ordered stacks. And this stack formation happens very quickly. Within 20%, we see that most of the rings are forming this kind of well-ordered states. And this local ordering also increases very much, which means the rings themselves or these clusters themselves tend to become very ordered as compared to randomly distributed. So our idea is that ultimately when it is very diluted, it will form a single stack. I will come to this later in more detail. So we analyzed how the stacks will look like. So first we calculated what is the lowest eigenvector for each ring, and then we calculated that if there are two rings with this with this lowest eigenvector, what their angles are. And within some particular cutoff, we determine that okay, if these angles are effectively parallel and they are very close to each other, they are forming a stack. And we defined a cutoff for at least 5 or 10 rings form this kind of stacks. Then we called, okay, this is a stack cluster has formed, and then we can say that all rings inside this stack cluster are essentially stacked against each other. But if that is not the case, then if there is like a 2 or 3 member ring forming stack, we don't count it as a stacking effect at all, because that is just some random event that is taking place. What you observe is that within 10% dilution from 20% itself, there is a drastic decrease has happened from this amount of unstacked rings. So basically at 0 and 10%, there is a lot of rings that are unstacked, but the moment we dilute it, beyond 20%, most of the rings starts to form the stacks of 10 rings or more. And there are still some fluctuations are here, which I will come later. And so here I want to highlight the dynamics of the systems. And you can see that so the bottom part is for the flexible rings, top part is for the stiff rings. And for the stiff rings, at the lower concentration, it is still very much glass-like, where the dynamics is very poor, and then it slowly starts to rise, becomes more gel-like, and then at 80% it is mostly fluidous mixture. On the other hand, for the flexible systems, I find that for the very low concentration of these flexible rings, there is a kind of a subdivision takes place. And more we increase the dilution, it becomes very much diffusive. And this kind of subdivision was very interesting to us because we thought that this might be related to the movement of these flexible rings through the bunch of stacks of these stiff rings, where you can see the stiff rings columns are forming. So if the flexible rings are moving through these particular columns, one would expect this kind of subdivision is taking place. Another part is the threading. So we wanted to understand how the threading decays with time with the dilution. And for this system, we find that after about 50 or 60%, there is a sharp decrease happens in threading. And this is because for this kind of system, we can see that up to 40% or so, there are a lot of stacks, they are interpenetrating each other. So the bunch of stacks are coming in between the other stacks, and that is what is driving the threading up. But after about 60% or so, this kind of overlap between the stacks, they do not take place. So stacks are more parallel to each other, and therefore there is not much threading is happening. So we are effectively melt the topological glass. Now we look at the cluster size distributions. So the idea is that the more dilute the system is, the more rings will form stacks. And now, however, of course, the number of stiff rings are decreasing, so we have to normalize the cluster sizes. And we show that as we dilute the system, most of the rings are forming stacks. Ultimately, when a single stack will form, everything will be at the far right end of this graph, which is 1. But already at 80-20 mixture, you can see that most of the rings has moved to the right side, which basically means that entire ensemble of these stiff rings are forming stacks with dilution. And we also measure how does it dilution controls the angle distributions of this cluster. Basically, what is the local ordering? What is happening at the local ordering? And to measure that, we calculate the largest center of mass vectors between each stacks, and then we calculate the angle between the stacks. And we find that for the pure system, its very broad distribution is there, with a maxima is roughly around 90 degrees, which means that most of the stacks, although there are stacks formation is happening, they are more disordered. However, as we increase the dilution with flexible rings, the graph shifts toward the left end, and they are much more ordered now as compared to the pure systems, which also you can see in these graphs that the pure system is much more disordered stacks are present, but as we increase the dilution, the stacks become parallel to each other, so they are much more ordering. Also at the ring level too, we see that this ordering is happening, which is essentially the same plot as this one. We see that for the pure system there is a broader distribution, and distribution decreases when we increase the dilution. And then we looked at the stability of the stacks. So basically we wanted to see what is the stiffness difference required for these stacks to form. And for that, we took one of the structure from the 80-20 mixture, and then we increased the stiffness of the flexible rings. So first it was 1, then we increased it to 5 and 10 and so on. And what we find is that up to 5, this structure remains stable, but moment we went to 10, this kind of stacks is down, because this flexible, or they are not so flexible anymore, so they kind of compete with the stiff rings. And this competition you can see here that for this purely up to this 5 stiffness for this flexible rings, it is still, most of the rings are unstacked, but moment we increase it to 10 or so, the number of unstacked rings decrease for these flexible systems, and opposite happen here. Some of the rings, most of the rings become unstacked for the stiff system, which essentially means that this solvent, it's not the solvent, it's called the flexible ensemble, is becoming more ordered, and at which is competing with the stiffness, with the stiffer rings, and so as a result these stacks are breaking. And you can see what is the typical shape required for this flexible system, which basically controls this kind of stack formation for this system. What is happening is that for k is equal to 1, it is much more globular shaped, which is helping for the stack formation, but for k is equal to 10, they are becoming much more planar or rod-shaped structure, which does not allow these stacks to form for the stiffer system. So this shape asymmetry has a direct contribution to the stability of the stacks. And then we try to understand this kind of whether the single stack is possible to form at very large dilution. And to understand that, we performed a pressure hysteresis experiment. Basically, we earlier, as you can see, there was some fluctuations was there at the large dilution. But whether this is a kinetically trapped state or there is a thermodynamically stable state is possible, that was the motivation for our this pressure hysteresis. So basically what was done is the system, we have taken a artificially created single stack system, and we decompressed up to a very low pressure with some rate, and then we calibrated it at that pressure, and then we compressed it back to our previous pressure. And this is the result of it. So we slowly decompress it, it becomes random, then it forms the stacks on its own. So the self-organization that takes place is essentially spontaneous. It looks like 2 stack, but it is essentially single stack because of the periodic boundary. So this experiment basically tells us that this stacking is essentially spontaneous, and at the very low, very high dilution or very low concentration of the stiff rings, it is possible to form a single stack within the system. So this is a thermodynamically stable state. So to conclude, what I find is that the stiffness plays a very important role in this topological glass formation. And if we adjust the stiffness and pressure, this topological glass can be found for small chains. We don't need very large chains as was predicted from the pinning model. And this binary mixture with a large stiffness difference is basically, it forms a spontaneous self-organization of the stiff rings, which is very novel and different compared to the linear chases. And the stability of the stacks that depend on the stiffness difference, as I have shown, there is a critical stiffness range is present within 5 to 10, which allows this stack to form. They also depend on the pressure and on the shape asymmetry of the flexible rings. And we also recently tried to replace these flexible rings with crowders, and we found that they actually destabilize these stacks, which means there is some criticality, there is some interesting behavior is present for these flexible rings, which is controlling the stack formation. And that is not just the globular shape, there is might be some dynamical explanation is there too. And from the pressure hysteresis, we have proven that these clusters are essentially thermodynamically stable states. And for the outlook, there are recently interesting papers was published where they saw the stack formation for these rings which are charged, essentially is a polyelectrolyte rings. And they have seen that this kind of stacks also form in this kind of electrical and polyelectrolyte cases, which would be very interesting area to cover. Another aspect is the active rings. So when you introduce active systems, whether this kind of stacks will still be stable or not, that will be an interesting area to study. And we are also looking into these confined systems where you introduce very thin film type of confinement, and we can study that what kind of stacking behavior will present in these cases. So lastly, I will thank Vani madam and Pinaki sir for designing this project, and IMSC for providing me the funding. And thank you very much.
Thanks, Brajesh. Questions?
Just wondering, is the sizes homogeneous when we are synthesizing these ring polymerization things? I mean, the size of the polymer. Is it homogeneous? I mean, experimentally when you are synthesizing this?
Yeah, experimentally it's supposed to be homogeneous.
How do you control, I mean, the size?
I don't know the experimental detail. I think there is related to some temperature related factor is there, but I'm not sure. I don't know the experimental details. But it is difficult to control, mainly because it might form, when you synthesize in long chains, it might form knots.
Right, because there is possibility of the different sizes will be. So, okay, the second question is, have you tried any heterogeneous, size in your molecular dynamics? So, whether the same size is stacking or maybe is intermining between the different size of the polymers? Or have you tried anything with the
No, I have not tried, but we guess it will be different because it depends on basically the stiffness ratio is related to the persistence length. And when you use a large system, we have to use much larger persistence length, and therefore this difference in the stiffness would go up. So yeah, I expect there will be difference when you use different ring sizes. But we have not tried that, but it will be different.
Okay. Thank you.
Any other questions? So I had a question. So, see, you said that when you increase the stiffness, the threading increases, right? So how do you sort of explain that? Is it because it remains in an elongated fashion when the stiffness is small?
So basically the structure of the rings become much more elongated, as you said, and also more plate-like. So what happens is, if they somehow penetrate into each other, it's very difficult to pull out. Because of the stiffness, they does not have the flexibility to bend itself and then pull out so easily. So for the very stiff system, this kind of threading becomes very obvious, because somehow if you created this kind of threading, it will never come out.
Right.
That's the control.
Yeah. Kabir?
So what is the effect of the interaction strength between the monomer units? Have you checked that?
So we use the traditional
Yeah,
Granollers model.
WCA, but like now if you decrease the temperature or increase the attraction, do you find some sort of phase separation occurring?
It would be interesting, but our main motivation was to see the topological effects, and there this interaction set will not matter because that is very small cutoff. We are doing like, I think WCA is 1.12 or something, that is really small, and these are taking place in for a 100 Mach system that is roughly the size of 16 or so.
So the constant temperature that you've used, it will not make a difference if you sort of change the temperature.
It will make a difference. It will make the system slower, definitely. But the thing is that what I wanted to highlight is we are not looking into the temperature or interaction strength that usually controls the glass formation. We are looking into the fact just by changing the shape of the rings, whether one can form a glass. So one can definitely change the interaction strength and temperature, and one will observe different dynamics, but the topological factor will be the similar for all cases, that by changing the shape there will be a control. on the diffusion.
I see. Okay, thanks. Yeah.
So the threading algorithm you have, can it be applied for detecting the events between linear chain and a ring chain, for example?
Yeah, it can be done. So basically this threading algorithm calculates the area of the each ring, and what I measure is how this particular bond vectors for each of these other rings are penetrating into these surfaces. And so for linear chains, we have the list of bond vectors, and we have all the list of these areas or these triangles, and from there we can calculate the amount of threading for linear chains.
Okay, so if there are no more questions, let's thank Projesh and all speakers of the session.
Thanks, Sumesh, for chairing the session. So we break for lunch. Lunch is outside, and we come back at 2:30.
Hello, mic check, check. Hello, mic check, check. 1, 2, 3. Hello, mic check, 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 check. Hello, mic testing. Hello, mic check, check. 1, 2, 3. Hello, mic testing. Hello, mic testing. Hello, mic check, check. Hello, mic check, check. 1, 2, 3. Hello, mic check, check. Hello, mic testing. Hello, mic testing. Hello. Hello, mic testing. Hello. Hello, mic check, check. Hello.